Okay, so this is class is going to be about PennyLane. And I also upload some code. Yeah, why do we want to cover PennyLane? Because it's a useful framework that actually you can use machine learning, and then you can code quantum machine learning. Yeah, it's very well developed. And I think the nice thing is they have a lot of demo. If you go to this, let me see if I can go there. Yeah, see. First, maybe let me go to PennyLane. Yeah, so this is PennyLane's website. It has a lot of demo, which actually cover a lot of topic. This could be your final project. I mean, you could use PennyLane or Qiskit. And let me see. Explore demo, right? They have tons of demo. Cover a lot of topics. If I click this, you can see a lot of demo. How to build compressed double factorized Hamiltonian. Solving system of linear equation via HHL using QRIS. I don't know what this is, but this is Catalyst is also PennyLane. So there's a lot of very useful, quite advanced demo. They also have demos that actually demonstrate the result from papers. So you see there's 172 demos. So I can just randomly click how to use noise model in PennyLane. We cover Qiskit. You can actually introduce noise in the simulation. So this is how you do it in PennyLane. So I just randomly click this noise. I haven't looked at this before. Yeah, 175. How can you study everything? Uh, if you finish all the notebook, you will probably pick advanced. Um, right, so there's noise functions, polarizing channel. We cover this, creating noise model. So I feel that this is very useful framework as well. Yeah. So you will you could use this to do your research. Yeah. So I'm not going to advertise too much for them. I mean, it's a useful tool. Yeah. And it can also connect to backend. If you do your coding on PennyLane, you can run on various backends. Okay. So maybe let me go back to the slide. Yeah. And there are also a lot of YouTube tutorial that they have, and also others. Okay. To install PennyLane is very easy. Just pip install PennyLane. It can also use with GPU. If you have GPU, then it will speed up a lot of computation. Yeah, so I mentioned, PennyLane has actually their YouTube channel has a lot of video tutorial. So this is one example. We're going to learn this today. Like this, define a queue node and then some device. You define a device, and then there's a circuit, right? You already know Qiskit, so writing the circuit is very simple. There's a poly X. They call this wires. Right? This is a qubit 1. CNA is between 1 and 0. So you write this, and you have rotation, RY, angle, and wires. And then you do some expectation value for poly Z operator. So that's, we're going to give more detail. And they have this very useful thing, codebook. Let me open that. So they have codebook and a lot of exercise for you to go through. Let me go to the website. If you want to learn full scale of PennyLane, you would need to go through at least these codebook. Using PennyLane. Codebook here, so it's here. And sometimes they host some challenges. You can compete in their challenges and you can win some award. Okay, this is the code book that I showed you this snapshot, right? So if you click, you will see a lot of code examples. Maybe, okay, let me just quickly click. I finished all the code exercise. So the answer will be here. So let me not reveal the answer. You can, there are some example, they ask you, okay, do this, do that, and write your own code. Similar to the lab that you have worked through. Okay. The Qiskit one. But this is like they break into module. So they break into module. There's some introduction, algorithm part, application, fault tolerance. So once you have finished this, you have learned a lot in quantum information, quantum computation, mostly quantum computation. Okay. Yeah. So I found out this sort of right before, I mean, maybe a few weeks before the break. Yeah. And I worked through all of them in order to teach PennyLane. Okay. So yeah, once they call this code exercise, code exercises. If you finish, then you see all the chat. Okay. Yeah. Okay. So today we're going to start with an example actually from Dr. Serrano's YouTube video. You're probably familiar with his YouTube now, where he sort of illustrate his notebook and Qiskit. And maybe we're going through the PennyLane Fundamentals. This here, this is the one that they have 4 different sections. This is this one that will give an overall picture of what PennyLane is. Okay, but if you really want in depth, you can go through this. Yeah, go through all the code on your own. So you will need to create an account with them, and then you work through the exercise. Yeah, but I can say I'm qualified to teach because I work through all the code. So this is the proof. Check. And I have, yeah. And the nice thing is the code book, you work through yours and you can submit to see if the correct. After you submit and it's correct, then you can compare with their coding. So it's useful to see how other people do it. First, you work through it, and then you compare with the experts. Yeah, and sometimes it's not necessary every code exercise is straightforward. Sometimes requires some thinking. Yeah, and require you know actually what they are talking about. So if you work through the code book, you probably the next step what you do, you probably would participate their challenges. Those probably would have more advanced topic. Yeah. Maybe that's download the notebook that I posted. There are at least two. Uh yeah. Have you downloaded? Let me go to the okay. So this is the code book posted on our white space. You can go there, download, I think okay. Lab 4, lab 1. Actually, I'm trying to go through all the lab book that you guys are going to present. Okay. PennyLane, this is the this. Okay, I have not. Okay, let me. Not showing the paper. Okay, there we go. Basic. Okay, let's do this one. This fail to fetch. Okay, let's do it here. The PennyLane basics. Okay, it's from Dr. Serrano's video. You can click and watch his video. Yeah, and you can play along. So once you install PennyLane, it should be easy to install. They often import PennyLane as QML, quantum machine learning. So they usually do this. I have no module. Let me see. Maybe I have not. Let me restart again. Restart my kernel. Okay, let's do this again. Okay, we can load and this should be fine. Okay, let's import PennyLane as QML. So we're going to do the first circuit and we define a function. You can see here. We define a function and we apply X gate. So the X gate you need to say is poly X. So QML dot poly X. And wires equal to 0 is qubit 0. And you do the Hadamard QML dot Hadamard wires equal to 0. Okay, then return QML.state is the state of the qubit. So be a vector of two components in this case. So let's define this. In order to run this, you will need to have something called a device. And the often used one is default.qubit. Okay, this is the name of the device, and wires equal to 1. You only have total 1 qubit. Okay, and then you also need to have a Q node. So you define QML.Q node. Then this is the function that you define, and this is the device. So this Qn is QML.Q node. Okay, and then you can print. You can print as in Qiskit. So when you print, you will use QML.draw of the function. Well, in this case, this is Q node. The Q node is actually implemented this function, Q function. Okay, and with the argument, whatever argument Q function has, you would give it to Qn. File change. Yeah, so okay, so but this is how you print. Of course, this is using text. As we have seen in Qiskit, there's also a matplotlib version. You write as fig x equal to this draw underline MPL. Similar way as above. Okay, I already drew that, so when you draw it, it looks nicer. Okay. And in order to use this function, well, in order to be able to evaluate, you use this Q node, Qn, and you say as V equal to Qn basically is running this Q function. Okay, running this Q function. But using this Q node to run that. This is slightly different from we've seen in Qiskit. So when you do that and return, the state is this one. We know this state exactly, right? What is the output of the state? So 0 apply by x become 1 and Hadamard become minus, right? So this is the minus state. This is the first circuit that we see now. But there is some inconvenience. You have to define a function and then define the Q node, right? And then in order to run it. So you can use this property decorator to define a function that has this property Q node. So again, there's a function, there's a device, okay, and you decorated this function Q. I write as Q2n, the same function. What do I? Do you want to override with the version or load the version? This override this override. Okay. So you just decorate with this add QML.Q node device. Then you write the function as you did before. Basically, you can decorate this with that Q node, lowercase Q node, QML.Q node, the device. Then you can directly run this, right? Qn2 function, you just print and this the minus state. Any question on this? It's slightly different from Qiskit. But Qiskit also has different like simulator, real backend, right? Noisy simulator or like using air simulator, they're different. So basically that's corresponding to that. Okay. So it returned the state, but you can also return the probability. So when you return probability, you just say return QML.props. This is returning the measurement probability as 0 and 1. Yeah. Okay. So in the circuit, somehow it just add this measurement at the end because you return something. But when we return state, we actually didn't measure it. Okay. So I hope I run this. Okay, yes. I also did this. Okay. So so I define another function with Qn3 which return the probability. Okay. So you know it's minus state, so it's 50-50. Okay. As in Qiskit, we can actually get the operator and get a unitary, right? So here we can also get a unitary, and we can extract from the circuit. This is from the circuit, and you just say and QML dot matrix, and this is the function, and that's the argument that you input to Qn3. It would ignore the probability. It would just consider the second part. Okay. And we know this is like Hadamard x followed by Hadamard. So Hadamard is 1 over square root, 1 over square root, 1 over square root, minus 1 over square root. And there's also, so it times the x that will give rise to this. Okay. So Qn2 is returning the state, Qn3 is returning probability. But if you do the same matrix extraction, it gives the same thing. Okay. Even the earliest one, Qn, this Qn. Okay, Qn, you can also do that. You can try other things. Actually, I don't know if I do this on the one that does not have decoration, right? This is the circuit, the first circuit that we have without decoration. Q function, would it give us the matrix? I don't know. We could try this. Q function. It maybe it would return error. Yeah. Right. It would tell us why order is required matrix. Oh, corner functions. Raise this. So yeah, we don't use Q now, so that's why it won't be able to evaluate. Yeah, so there are a lot of things that you could try and see if it work or not, like this one. Okay, so this won't work. So we can just put a remark. If this cannot be evaluated. Okay. Okay, so here, basically what's introduced here, there are a few different functions. We return state, we return probability. So here, you can actually just define the circuit part. Right? So this is what is introduced here. Circuit has the x at Hadamard, and then you define, okay, if I want to have the state vector, I just run the circuit and return the state. Right. So you print this, we know it's minus state. Or if you want the probability, you just put the circuit part in and then return the probability. So circuit, that define the x and Hadamard, and then you return the probability. So you can just do that. right? And you can also do what we did. Ah, okay. So I think this error here can be fixed. This error here can be fixed because it complained wire order is required. Okay, so it's not because it cannot be evaluated. So let's say y equal to 0 and see if it works. Yeah, it got expected. There was this here. Or maybe it has to be. Oh, I see. It's a list. Y order is not one. So you have to use Y order. Y order as illustrated here. It's useful to have the notebook like organized so you can see. I've seen this and I forgot, right? So you just need to use Y order. But at least I was expecting the question here. Can we do this? Won't work if no, it's not. Okay, it worked. So now it's working. So remember to add wire order matrix. Okay. Okay. So as in Qiskit, you can also have shots, right? So you can emulate the shots like you as if you were running the quantum device and make measurement. So it can also do that. To do that, you will need to define a device. So QML.device, this is like default qubit. And okay, so I have one wire and I have 100 shots. In order to run the shot, you need to do this here and add shots equal to 100. Okay, so I decorate with this node and the device is this. Okay, so I'm going to sample this. To do that, I run the circuit, right? And I say I'm going to return QML.samples. And when you sample, you need to say which wire, which qubit. It could be there may be 10 qubit and you only sample the first qubit. So you do this. So we define this QN samples. So you run this, and what it does is print out a list of, okay, I did not, QN sample is not defined. Yeah, there's a S, missing S. But somehow, somehow I have the the result. Maybe I changed it. I think I changed the name. Right, so it was sample. And so the first I get 0, second I get 1, etc. It give you a sequence. And you can count. You can use numpy, count non-zero. Right? You could also count when it's 0 or 1. I mean, you know this should add up to 100. So 52, 48. Okay. Of course, you can do the probability, but when you're doing the probability, uh, as before, we return the probability, right? The probability, because this is a finite shot, right? So when you return the probability, it really just calculating the statistics. So if you run again, the probability may be different. So if I run again, right, it's different. So why is that? Why is the probability different? But why is previous code, I always return the same probability? Can you think about why is there a difference? because we have the finite number of samples, 100, right? And previously we didn't specify that, so it would calculate the exact. And here we have 100. So when you do the 100 samples, you do it this time, next time it would not be the same because the statistics. Okay. And if you are using this device 2 has shots, and you want to ask it to return the state, it will not return the state. It will tell you that this is error. Okay, if I do insist to return the state, this is incompatible. Okay, let's see. Measurement not accepted with finite shots. Okay, okay, measurements state not accepted with finite shots and default qubit. Okay. So yeah, so this is used for doing the shots, just like we do in Qiskit. We want to do simulator with finite number of shots. Okay, previously I show you it returned this 0101 string, right? So you could also sample with respect to operator. Like if I want to use poly z, poly z's eigenvalue are +1 and -1, right? So it will sample the plus minus 1. So when you return, it will return +1 -1. So this is because you want to sample this operator. Okay, so let's sample that, define this, and then do this sample here. And you can see it's, each time is different. It's a string of 1 or -1, right? And you can still count if the samples equal to -1. So with this, you can actually calculate the probability or expectation value of the observable just by counting how many, right? So you could do this. So we can get the observable by doing this. So let's see if it's +1 or -1. So you just add up. So if it's -1, we multiply -1. And if it's +1, you just add this. Then we divide it by the total number of shots. Okay. We know it's 100, but if you want to be like really general, you could just add them up. So this will be expectation value. And we know it's a minus state, so the expectation value should be close to 0. But it's not quite 0. And if you do this a different time, the value would be different. So you can actually sample this. You can do it many, many times and do the histogram to see how this distribution. Okay. You can also do the X. Okay, we can do also do the X. And it's because this is minus state. So even finite statistics, it always get -1. So we can also do the expectation value. Of course, this one is really trivial. This one is also trivial, it's -1. Okay. So this we do it by hand, but you could use the built-in function expectation value, like what we are doing also in Qiskit, like EXPVAL. I think they use similar. Okay. So this just return expectation value of this operator on which qubit. Okay. So of course it's -1. This is defined as X, so we can also define the Z as we did. This very easy. Sometimes is plus, sometimes minus, because it's equals to 0. Okay. Okay. Yeah, so we compare with different device. This device is with shots, right? If we compare with this ideal device, we'll always get 0. We will not get any fluctuation because this is ideal, right? Okay. So any questions so far? We are doing this 1 qubit and maybe slightly boring. We just maybe move on with the 2 qubit circuit. So let's define this circuit 2. Let me see if we can plot this. QML.draw. Let's use the MPO one. Circuit 2. Okay, we can draw the circuit. So this is the circuit. Well, they usually assign this so that, but it's okay if you don't do that. Okay. This is the Hadamard and then control. Now this is creating a Bell state. By now this should be very natural to you, immediately recognize. And you can return the state. Return a state value. Okay, here I'm drawing this Q node. This QN 2 qubit. Okay. The better one is with, so the text looks not so good. So maybe I'll just convert this to MPO. Okay. It's okay, I don't assign it big. And so if you draw the circuit on its own, right, it would not add the measurement. But if when you are drawing the circuit where this function has return, it would have measurement. Doesn't matter what you are returning the state or probability, it would draw the symbol. Okay. Okay, if you return the state, we know the state is 0, 0 plus 1, 1, right? So that's why you have this 1 over square root 2 and 1 over square root 2 at the first and the fourth element. Okay, now we could also do the expectation value. This is 2 qubit expectation value. So we write ZZ. So you will write QML dot poly Z wire 0 at QML dot poly Z wire equal to 1. So this is ZZ operator. Okay. And we know 0, 0 plus 1, 1. ZZ is expectation value 1. Because ZZ is a stabilizer. Okay. Yeah, so you should get 1, but this is like machine precision. Okay. So this is 2 qubit. At the level of circuits, really easy. You already know. But if we just use this example to learn the PennyLane language. So if you have parameter, you have this rotation. It's actually this circuit below. So you have a rotation instead of Hadamard, you have rotation, and you do the control nut, and you evaluate, for example, ZZ. Okay, and depending on the angle, the value may be different. So this is at pi over 3, x rotation. So what about other value? Let's say 0.5. Still the same. 1.2. I think so. We can actually estimate this. So this rotation here put into okay, cosine 0 plus sine, and then if you do this C naught, so we cosine 0 0 plus sine 1 1. So still stabilizer. So that's why it always output 1 ZZ. But if you use X then it will be different. Okay. So let me see if there's an example. X. Okay, let's define another function. So to see the X. Okay, so let's evaluate instead of let me say 3. Let's evaluate XX and see that the value would change as a function of, let me call 2B, 2A. Okay, 2A. Because I don't know whether I have another function defined below or not. Okay, so let's do this and print evaluation at this 1.2 value. Yeah, so we get so this one is 0. You could ask why it's 0. So the state we get is roughly A 0 0 plus B 1 1, right? There's A 0 plus B 1 1, and we are evaluating XX. Let's just point this out here. So the state output is cosine 0 0 plus sine. Oh, there's I think there's I 1 1. Nice. So if you evaluate XX, then this will be cosine 1 plus I sine 0 0. Apply X, and then you evaluate the overlap of this one. So this is XX would be I sine cosine. and minus, oh, yeah, minus I sine cosine. So it's 0. Okay. Yeah. But we could try also like you could change this to Z operator, then it would probably break the symmetry. Then won't get something 0. Okay. Right. So this here, let's just say B. Yeah, so whenever you see something that's 0 or 1, you need to that those probably are not accidental. So you would need to see why is 0. Okay. We have this, and then let's print to B. And then this again is 0. So let's do something else. Y. Okay. Y, I'm sure with something non-zero. Okay. Okay. So the next is this is return state. I think I already evaluated this. Probably circuit 3. Let me just check it. Okay, this one I have not run it. Okay, so this is just to output a state. And we already know the state is a cosine 0, 0, plus I sine 1, 1. Okay, so draw the circuit. We already did above. Yeah, also here. Okay. When you draw the circuit, even though it has argument, right? You still need to input the argument, some random value. Otherwise, it would have errors. So if I don't do this, if I don't give it any argument, then it would complain. It will complain. Unless you in the default, unless you design a function that has a default value, but you generally need to give a value. Goodbye. Okay. Okay, so they also have these gradient, right? So we have this angle here. It's not shown in the diagram, but there's a theta here. We can try to evaluate and then take the gradient, and in order for us to know what is the lowest. So they have this gradient or Haitian you can use. You can take a look of their documentation. Let's see. It's actually easier just to Google it. So yeah, so you will do a lot of this documentation searching to see what this is doing. So for example, gradient, there's a parameter shift Haitian. For certain type of circuit, when you do the derivative, actually you can use a parameter shift. Yeah, so maybe some other time we can talk about that in detail. Okay, for this particular function, transform a circuit to compute the parameter shift Haitian with respect to its trainable parameter. Okay, this is the Haitian transform to replace the old one in a new. return type system. Okay, use this transform to explicitly generate and explore parameter shift circuit for computing a Haitian Q node directly without computing the first derivative. For second derivative of more complicated cost function, please consider using your chosen auto differentiation framework directly by chaining gradient information. So yeah, so the nice thing about PennyLane is it has built-in. You can let it do the automatic differentiation. Right. So you can look at these. Q grad, return the gradient as a callable function of hybrid classical. I think it used JIT to do that. So the parameter shift rule, let me just basically say that if you want to take the derivative, right, usually in the classical, you do the f of x plus something minus f of x minus delta and divided by 2 delta, for example. And in certain circuit, for example, a single qubit with rotation angle, the parameter shift is really taking that angle. I think it's at pi over 2 minus the evaluation of the angle that subtracted by pi over 2, and maybe there's a factor of 2. Yeah, and you don't do directly derivative. You don't take the numerical derivative. So that's called parameter shift. Maybe I can see PennyLane parameter shift, I think. Okay, there is a parameter shift here. Oh, yeah. Okay, so it's here. It's because the sine and cosine has this nice property. Yeah, so there's more technical explanation. So maybe I'll just point you to this, and then I copy the link. So it has derivation here. So you have parameterized the angles, and the angle has to be of this form, e to the I gamma times h. H is Hermitian operator. That is like Pauli or particle Pauli. Okay. So I won't go through the derivation, and this shows you that the derivative at the end, right, this is the simple thing that I just said. So you add pi over 2 angle minus the value at theta minus pi over 2 and divided by 2. Okay. Okay, so that, yeah, having said that, I think, let me see if they didn't have, maybe they have an example, but yeah. Gradient parameter shift, yeah. With this, then it's easy to evaluate the gradient. Okay, so that, yeah, so next is to use their built-in gradient but parameter shift Haitian to compute the Haitian. You could also use Jacobian. So we just take a look of, we already took a look at this, maybe JML from Jacobian. Internal Jacobian as Cordova function. Yeah, this is using AutoGrad to do that. Yeah, so in PennyLane, it has its own NumPy version, so that would allow you to do the gradient. Yes, it's here. Okay. Oh, let me accidentally close that. Okay, so this is the last part of this notebook. Yeah. Okay, so in in um in a word, this PennyLane allow us to do really simple differentiation, has built-in, yeah, has built-in functions to do that. Okay, so you can just, oh, I have not defined. It's not defined here. And you could evaluate using the shift Haitian, or you could use the Jacobian. So this shift Haitian using the parameter shift rule, and Jacobian use the auto dip to do that. Okay. Any questions? This is useful in doing the BQE. So you want to update your parameter. There is also something, this is not in the original video, but I find that is something that we should introduce is the mid-circuit measurement. So mid-circuit measurement has this diagram, right? So I have similar circuit, Y rotations, control nut, right? If I measure this second qubit, I want to do a Y rotation here, and then I measure qubit 0 finally. So that's the circuit here. So how to do this is you say M0 here, QML dot measure this qubit 1, right? And then you would do the conditional rotation. So what the function allow you to do that is QML dot cond, COND, M0, and then you do the QML RY. RY has Y angle on the wire 0. Yeah. This will be conditioned on the result. If it's 1, you do the rotation. You can take a look at this. This is similar to our Qiskit if test. Okay, so condition. There are also other like here. If the first, let's see. Condition expression that may involve in the mid-circuit measurement. Example, similar to here. Okay, this example is slightly more complicated. it measure qubit 0 and apply qubit 1 with condition like M0. It also measure qubit 2 and then do. You could use other value, right? So this will assume to be 1, you do the operation. But here you can say M1 equal, if M1 is 0, then you do this. Okay. Okay, I did not close that, but okay. Yeah. So then you can evaluate these functions. So this return the probabilities distribution. Okay. Okay. Yeah. So there's a comment that if a device does not support circuit measurement, then this Q node would apply the deferred measurement transform the circuit. So if it does not allow you to do the classical control, then it would make this quantum. Remember when we were doing the teleportation, maybe in last semester or this semester, we have a teleportation code. We could use the control gate to delay, right? Quantum control gate to delay the measurement at the end. So to do that, and you could explicitly write this deferred measurement. Okay. You can also take a look of this. It's always a good idea to check with the documentation. Okay, deferred measurement. On a function transform that substitute operation condition on measurement outcome to control operation. Okay. Yeah, this is what I said. If a device does not support this circuit measurement, natively the Q node would apply this transform. Okay. So I think this is a quick overview of PennyLane. Okay, with the knowledge of Qiskit, I think this gives you an idea that you can quickly apply your knowledge of Qiskit and apply to the PennyLane. It should be not so difficult compared to if you were learning PennyLane from scratch without any prior knowledge of quantum programming. Okay, so next, you could look at the code book as I show you. And I did upload a second notebook. Which may have something that is similar. Let's see how much we can go. This, let me quickly go through. I think I might have, yeah. I think I've taken the material from the code book. So there's a fundamental, right? There's one that actually give you a quick overview of PennyLane, which is this one. PennyLane fundamental, right? As I promised from the slide, we'll cover this for as well. So I basically take some codes from there, and they have some exercise, right? And I think I mostly use my own answer. So I didn't use their provided answer. Let me see. Is this one? Yeah. From gate measurement to variational quantum circuit. I think this one has more because it combined these four code exercise. Yeah, so maybe I pause here to see if you have questions. So if you maybe let me not go through this here in this class, but maybe next class. So then maybe the presentation of the lab will be next week. We'll start with lab 1 first, and then lab 2, and then lab 4. Anyone from group 1 here?
Yes, I think we're both on Zoom right now.
Okay. So yeah, so maybe you can present next Monday. I can hear them because I'm so let me see if I can keep speakers different from the
Is group 1 lab 1?
yeah, lab 1. Yeah, I think they are both yeah, they're both there. Group 1. Yeah. They're both there. And which group is yours? Yours lab 4, so you'll be the third to present. And I can present the mitigation. Basically, the mitigation one is similar to what I covered. These how you put these options. And for that lab, actually, they gave an example of code, and then you just insert the options. So that's fun. I can do that. Lab 4 also would have, yeah. Okay. So in the meantime, if you want to get ahead of the course, on PennyLane, you can work through this, register, and then this is the first. Try this first. Try this code book first. And that's what I did. But we'll cover that next time. Any question, more questions? Another comment is maybe you can start thinking about project. I also don't have limitation on what you do in the project. Maybe you work through in a demo and then present, or you actually have a project you want to work on something and then present, and you present your results. It could be Qiskit, could be PennyLane, could be if I cover Q-tip. I'm not sure I would have time, but if I cover Q-tip, you can all take the notebook, take the example, and then do something a little bit beyond what they have. Yeah, and I have not decided whether we do it each person present that. Maybe that's probably better because you're doing the group here. Maybe the final, this will replace the final exam, and you do it individually. Yeah, like you step up individually, and maybe half hour. Yeah. For this presentation of lab, yeah, you can take from half hour to an hour. It's okay. Yeah. The idea is we want to understand in detail of the notebook. Yeah. Okay, so maybe next time I'll try to cover this fundamental here, this one here. And then next week I'll let you guys present and see how it goes and how much we take. But I will also continue with some of PennyLane and maybe come back to Qiskit later. Okay. Yeah, so that's it for today. Okay. if there's no question, we'll stop here.